Yeah, darken my background a little bit so you can see me better. Okay, ladies and gentlemen, and Dr. Ashur, it's a great pleasure being here with you today. Please allow me open up the presentation so we can dive in. Okay, I'm going to share the screen now. Okay, good. Let me make sure that you have my uh, screen properly. Bear with me a few seconds. Let me reshare it again. The proper screen would pop out. Okay, good. So, is everybody seeing let me see, slide one. Everybody seeing the cover sheet of this presentation? Let me make sure that I check the chat box. Okay, good. Okay, Ed, thank you. I appreciate Ed Crane. I apologize if I'm not pronouncing it properly. Okay, so ladies and gentlemen, as I stated earlier, it's a great pleasure and honor to be here with you today, going over this seminar together, live seminar. Today, October 22nd, 2025, I'm in California, and I believe there are about 20 of participants. I'm not too sure. Generally speaking, I've been providing presentation to engineers, architects, probably about 20 years now throughout the United States and North America. And generally, the audience are engineers, architects, general contractors, government, and representatives, and so forth. So if there's any question at any given time, you can raise your hand, and I will see it on my end, and I will try to respond to it at an appropriate time. Today is going to be 2 hours long, and so we're going to discuss about various kind of failures and defects in the construction. So we're going to move on to the very first sheet. I just go through this very quickly. I've been a licensed structural civil engineer for over 40 years. I have investigated tens of thousands of structures from NASA to hospitals, universities, celebrity homes, uh, and so forth throughout North America. And I also perform as a forensic expert witness, and I have been designated as an expert witness in about 200 litigation matters throughout North America. Um, I provide these lectures as a continuing education for engineers and architects, so I can assist my colleagues in improving the knowledge in this field, so serving the communities in a more meaningful manner. Um, and that's it. Okay, let's go to the next slide. So I'm going to share with you my experience uh, through this webinar with the following five topics: building general and structural engineering issues, foundation system issues, structural framing members, patent and latent construction defects, and exploring deficiencies and failures in the structures. Let's go one by one. Building general structural engineering issues. In general, give me a second. Okay. In general, the structural framing or structural engineering issues, they can manifest themselves in terms of their performance in various ways. So when the structural is performing the way is expected, normally it has a life of like 50 to 100 years, whatever the building code, local building code is based on, and we're talking about in terms of a global building code, European, Japanese, Canadian, American, and so forth. So normally, when the issues with structural engineering, they can manifest themselves in various type of cases. The most common issues are settlements of the foundations, and then you come to the structural framing issues. Most of these are detectable by non-destructive testings. Here in this slide, I'm referring to a manometer floor survey, which is a common way to detect any latent defect on the foundation and structural framing. Let me elaborate on this for a few moments. You see latent is italic in this line. The reason is italic is because latent in law is a word of art. By the way, I went to law school for 2.5 years before I came into forensic engineering and science. I was much more attracted to science than litigation. So this comes from me from that background. Latent versus patent, these are two word of arts in law. A latent defect versus patent defect, they have two different meanings. Latent defect is a defect that a layperson cannot detect or identify. For example, if there are settlement in a building that is not noticeable by a human, or let's say there are, let's say the shear walls have issues and you need an expert to establish those defects and so forth, versus patent defects, which are obvious to anybody, to even a child. So, in order to utilize a non-destructive testing for latent defects in structural framing and foundation, which a lot of time comes to movement and displacement, a manometer floor survey is a way to go. And I will elaborate on that once we go through the rest of the webinar. The second way of dealing with these are cracks and distress on the exterior, interior walls, and ceiling finishes. So whenever there's the performance of the structure is questionable, most of the time they can manifest themselves with cracks and distress. And you can see these on the finishes most of the time. Obviously, sometimes you have latent defects in a structure that there's no evidence, period. You can't see anything unless you remove the wall, floor, ceiling finishes, and you expose the structural framing, and you find out, for example, okay, this moment frame is still member here, the welding has problems, there are issues with bolts or wood panel shear wall, there are issues with the nailing pattern or hold-ons or reinforced concrete shear wall, that there are issues with reinforcing and so forth. So, but generally speaking, normally, in majority of the cases, these defects are evident, and that was what triggers the investigation by the owner or the parties involved. Misaligned or sticky doors or windows or openings, these are the things that we observe when the structure is not performing properly. So this webinar, our focus is on common construction defects and failures. So we need to keep that in mind. There are a lot of areas in structural investigations, but in 2 hours, our focus is going to be on the construction defects and failures. By the way, I attend some webinars myself, and I noticed that sometimes the presenter they don't show themselves on the screen, and you just see the screen and you just hear the voice, and I tend to be a little bit curious. I like to see the person who is providing the presentation. That way I know it's a human, it's not AI or something. Today, if you go on YouTube, you can see probably 20% of today, recent YouTube videos are all AI. They are AI, and you just have to be quick to catch, because most of these that are published, they don't even get checked by the publisher themselves, and there are so gross errors in them that you can see. Anyways, so that's why I like to keep my camera on, so you can see me and we have some facial interactions and expression, and it makes it easier like a human rather than a robot or computer. Okay, so from the back in this third slide, from here we review this. Now we go to the foundation system issues. Okay, so we are breaking down this overall issues, structural issues, item number one, we're going to go foundation, and then we go the superstructure or framing. Okay. So now we are working on, we're going to review the foundation issues. So that comes to four subcategories: foundation system failure, soil movement or displacement, geotechnical engineering evaluation, structural engineering design. So I talked about manometer survey as a non-destructive testing on the previous slide. So this assists us on the verification of foundation. Obviously, it also assists us in the verification of the framing system on the upper levels other than the first level on the foundation. But this slide is focusing on the foundation. So generally speaking, for those of us who are not very familiar with the manometer survey concept, I'm just going to explain that in a very 30-second. Essentially, to do this, you have an instrumentation. You bring the instrument to the building and you check essentially the topography of the floor. You find out which areas are low, which areas are high, and you um, draw that on a plan showing just like a topography for the field. You show which areas are high, which areas low, and that way assists you to analyze what's going on with this building and which areas are high, low, shifting, tilting, whatever. So that's what we call manometer survey. You do it at the site, then you bring the data into the office, then you go through the process and compile the information, and you generate the topography for that structure for various levels, foundation, upper levels, and so forth. So generally speaking, what is acceptable, what is not acceptable for elevation differences? If you have a 3,000 square foot house, like a 50 feet by 60 feet, for example, what kind of construction tolerance, what kind of floor elevation differences are acceptable? It depends whether the building is new or old. By new, I'm meaning I refer to buildings that are at least, at the most are 10 years old. By old, I'm talking to building about 67 years old. Of course, I've inspected or investigated buildings. Okay, Ed is asking a question. If you allow me, Ed, I will answer your question in a few moments, sir. Okay, thank you. So I've investigated buildings that were, to be honest with you, now we're in 2025. Yeah, early 1900. Early 1900, yeah, over 100 years old. Yeah, there are buildings that people still live in there, they're still usable. So the deflection, the floor elevation difference criteria is not the same for those buildings in comparison with the new building. But the new building, this criteria is 1/360. This is not L/360. This is different than the building code deflection. This is not deflection. This is called angular distortion, and is 1/240 or over 60. And I explained to you how to calculate that. It's simple concept. So for older buildings, it can be 1/240. For newer structures, it should be at least 1/360. How you compute that is that you determine once you establish your topography, then you go various areas and you find out what's your worst case floor elevation difference. Let's say you have 1/4 inch and you see, okay, what's the most distance that you have this worst case floor elevation difference. Let's say you find out, okay, 20 feet, I have 1/4 inch floor elevation difference. Okay, so how do you calculate that? Okay, you have to multiply that quarter inch to 4 because you want to bring it to 1. Okay, so then that distance has to be multiplied by this same number, which is 4. Okay, so 20 feet, I have to multiply by 4. Then I have to multiply by 12 because the unit has to be inch. That gives me, so 20 feet times 4, that's 80, times 12, 2 inches, it's 960. Okay, so that value is 1 over 960. This angular distortion for a quarter inch over 20 feet distance becomes 9 over 960, 1 over 960. 1 over 960 is by far better than 1 over 360. The higher the number, the better. Now, in contrast, let's say in 20 feet distance, another structure I'm reviewing, and I have 2 inches of floor elevation difference. Okay, 20 feet, I have 20 inches. What would be my distortion and angular distortion value? So 2 feet, 2 inches, I have to divide that by 2 to make it 1. Okay, then the 20 feet, I have to divide it by 2 to make it consistent with what I did for the top value. So that would become 10 feet. Then times 12, that would be 120. 120 because I have to convert it to inches. So now my value would be 1 over 120. 1 over 120 is by far less than 1 over 240. That means my angular distortion is way below acceptable level. So when I write my report, I don't say higher or lower. I say worse or better because people get confused if I say it like that. So the higher value, the better performance. I've seen buildings, normally the buildings that I go and I have my Hewlett Packard calculation. I'm just doing this as we speak. So I'm old school. I only like reverse Polish. And Hewlett Packard does not make these anymore. You have to buy them from a Swiss company at Switzerland that they bought uh, this from Hewlett Packard to manufacture this, and they're like $600. You have to buy them from there, but I love them. Okay, good. So um, I've done building structures that were maybe, I don't know, 40 years, and I've had deflection. The criteria was like the floor elevation difference was like 6 inches within 50 feet. So I've seen structures with like 1 over 80, which is completely unsafe and unacceptable. It goes beyond unacceptable. It goes to unsafe condition, and I explained to you why it becomes unsafe. And I've seen structures that were like L over 1,000, very high-end structures that were like precision full elevation level. Okay, so that's what you're talking about the foundation. Now let's go to the next slide. We continue about foundation system failure, okay, or lack of performance, if we may. Okay, so here we have just a sketch, simple sketch of the. I put my phone on the silent, so no, no motivation. Okay, so just a schematic of a simple structure, one story, and this is one of the cases that I had many years ago, and was settled a long time ago. He went through the court procedure and everything. Okay, so this was in a case of a post-tension concrete slab, post-tension concrete slab on grade. So, you have so many different type of foundation system. You have pile foundation system, you have mat foundation system, you have shallow footing foundation system with a slab on grade, you have post-tension pile slab, you have raised floor foundation system, and so forth. So in this case, I'm going through a post-tension slab because they're very interesting. Post-tension slab, different animals, and you have to be very careful with them. Before I continue, if I may, I'm going to address the question that very quickly address the question that Ed Ryan or Crane stated. Can a laser level be used as well if there are clear line of sights? The answer is yes, but it's very difficult to compile a topography uh, um, um, plan for that. Laser gives you some kind of idea what's going on. If you want, you can use a ball. You can just use a tennis ball or golf ball and put it on the ground. And if the slope is really bad, the ball starts rolling. So yeah, but if you want something that is objective and scientific, um, um, floor elevation with manometer is the way to go. Okay, good. Because floor elevation is completely objective, and you can do it, and another company can do it. 10 different companies do it. The results are within like 5%. They don't deviate that much. Okay, so back to the slide. This building, it was part of a huge development, and a bunch of them had the same problem. This was in Northern California, a very nice neighborhood, not northern, maybe central, near ocean. Anyways, when they started their development, the soil engineering study was done. They determined that there's expansive soil. So the recommendation was to dig out about top 5 feet and remove, and then bring in the new material layer by layer, recompact per ASTM Proctor requirements, and then build the foundation on that. That was what the geotechnical engineering study stated. And but apparently that was not completely the case. Apparently, what I recall, because this is like 5 years ago, what I recall is that they removed the soil, but used the same soil again to fill it. And I think they were, yeah, the same soil, they filled it back in the same expansive soil, and they just recompacted. They just tried to save money because they were larger scale, like hundreds of homes. So then they put the post-tension slab, and then they built it, and then owners bought it. Our clients bought it, and then they started having problem. And you can see here, so excessive settlement due to edge heave. Edge heave. Okay, let's see, what's edge heave? Okay, when the edges go upward, the perimeter of the foundation, that's called edge heave. That's a terminology in construction or engineering. So essentially, the reason that you have this edge heave is that the moisture, the rain, once the building is built, everything is okay, looks fine, good. But over the course of months and years, rain comes, and rain comes from around the perimeter. It doesn't go to the center, right? So your soil on the perimeter, they're expansive soil, they're clay soil. As soon as they absorb water, their volumetric changes occur, and they expand. Once they expand, they push everything up. So the perimeter of the building goes up, and the center of the building stays down. So then this schematic is showing what happens. And now I'm going to share with you some of the actual photographs. Okay, so this wall, if this wall is running from is longitudinal wall, and is running from the front of the house in this side on the right hand side to the back of the house on the left hand side. So this wall that you see is essentially, I don't know if my mouse, yeah, my mouse. I think you can see my mouse now. Is that right, Dr. Ashu? Can you see my mouse before? If I was moving on a different, moving my cursor on a different, I have multi-monitor. So let me know if you can, okay, you can see my mouse now, but how about now? Can you see my cursor when I move? Ed is my assistant on this presentation. I'm honored to have you, Ed. Can you see my cursor now, or you can't see my cursor? Oh, okay. Because I have multiple monitors. Okay, I now you can see, correct? You can see my cursor? Okay. Thank you, sir. We should give a good discount to Ed. He's helping us a lot. Okay. So here, this wall from left to right, this right-hand side is the front of the house. The left hand side is the back of the house. So the wall is longitudinal, like about 80 feet long, and is running in the middle of the house. And the ceiling that you can see, the trusses are running perpendicular to this wall. Okay, the roof trusses is one-story house. The roof trusses are running perpendicular to this wall from left to right of the exterior wall. And you see what's going on here. If I can zoom in, if I can zoom in, yeah, you see the big separation, like 1 inch separation here, here. So in the middle of the house, you see this separation. Why do we have this separation here? I explained to you why. Because look, here, because of the heave and expansion, it went up. It went up. And look what happened here. When it goes, the perimeter goes up, the truss bottom core stays on the perimeter wall and is level. But what happened, the bottom keeps everything, all walls the same place. That's why you have these displacements in the middle. You see that the gap. So we go back here. This is that center. The center, the walls are anchored to that and supported on the slab. They're down, but the roof trusses, they go up just because of the way is displayed here. They're up because their ends went up. So that's how when you have improper treatment of the foundation, the soil, improper treatment of the soil, and not following exact recommendation of the soil engineer, that's why this problem happened. If they did follow the exact recommendation of the geotechnical engineer, we would have not had this. Why? Because the soil below this, it was removed. They were importing gravel or sandy material, whatever recommended by the geotechnical engineer, and would not experience volumetric changes because of the rain. So let's go through the other photographs. These are some close-up pictures that we can see. More cracks here, more separation. And this is a right now probably $1.5 million home. It's not the owners didn't pay little money. They paid a lot of money, and these kind of cracks are unacceptable. This crack here that you can see, it's this crack on the sliding door in the back of the house. It's a huge crack. You don't expect this in a 1-year-old home, $1 million back when they bought it, and these kind of separation. So we go next slide. Okay. So I just shared with you some of these, and then look at here, the window at the back of the house, this glazing cracked because of the displacement, forced the glazing to crack. Now, the next slide, we are talking about the soil movement. Okay, so far we were with back in the slide, so you have some objective what's going on. So we were talking about foundation system failure. Now we're going to go to soil movement. So we go back to this slide, the soil movement that that we're talking about. Um, just going over this concept when the soil exhibits volumetric changes, more specifically clay soils. So the clay soil, generally, this is showing, when you have a new construction, once you have rain coming in, it impacts the perimeter of the building, not the center of the building. So the swelling occurs, or that heaving phenomena occurs, pushes up the slabs upward. The center of the slab stays the same, doesn't go down, it just stays the same place. And you have this differential elevation that in this case that we were doing, because we did floor elevation difference, it was like about 2 inches or inch and a half. And if you recall in the earlier slide, I mentioned about the I mentioned about angular distortion. The angular distortion was way beyond below acceptable level. I don't recall the exact dimensions and numbers, but I believe was like, yeah, it was like 2 feet over like 20 feet the span. That's, if you calculate, that's like way below. I don't know off the top of my head, maybe 1/120, which versus 1/360 is way below. Anyways, so this is schematically is showing what happens with rain. And you have to keep in mind that water doesn't stay here all the time. Once the dry season comes, they go back down. But by that time, the moisture travels and comes in the center. So the center goes up. So in the winter, the perimeters are up. And in the summer, because it takes a long time for water to travel and cause volumetric changes. And so in the summer, you have the center going up. So this become a reverse. Yeah, like this is schematic. They all evaporated. So it's terrible, and it's a terrible cycle. It's going to happen every year just because somebody tried to save maybe $10,000 on $1 million home and went through all these legal issues and all these, inconvenience for these older owners. They were retired people that they bought their dream homes. Anyways. So essentially, here we are identifying the issue, as I stated earlier, removal and replacement of the soil, the way it was identified in the geotechnical engineering, and recompaction. Now, let me share with you something. There's a NASA scientist that has an expensive, large home, one of his homes, close to ocean near Central California. It's like a 15,000 square foot home. I don't want to go too much into the details, but he hired a licensed general contractor and he said, okay, build me this home. So they draw the general contractor did, his builder, did the home architectural. Then he used his own geotechnical engineer. The geotechnical engineer, it was similar condition. The soil was clay. The soil engineer didn't, when I went through his soil engineering report, it was terrible. He said remove, put back, but recompact. And that's essentially a no, no, no in geotechnical engineering. He was not a licensed geotechnical engineer. He was a licensed civil engineer practicing in the field of geotechnical, which in California is okay. You can do that as long as you have the training and education. You can, a civil engineer, because in California, let me step back. In California, you have civil engineer, which is a PE, like most of the states. I believe 90% of the states in the United States, they have a PE designation, which is a civil engineer, can practice structural engineering, can practice geotechnical engineering. However, in a few states, which I believe there are like six of states, like California, Washington, you have two other designations under the PE. Once you obtain your civil engineering license or your PE, then there are like several years of practice under supervision of a geotechnical engineer or a structural engineer and go through another 16 or 19 or 20 hours of exam again to once you pass, you qualify to be registered as a licensed structural engineer or licensed geotechnical engineer. So in California, we have these two other subcategories. And for example, if you're a licensed geotechnical engineer, you can get involved in certain critical projects that entitles you to do that. Or if you're a licensed structural engineer, you can do certain again critical projects that a PE cannot do that. They're not allowed to do those. You have to be a licensed structural engineer to do hospitals, emergency centers, schools, and so forth. And that's in the law, built in the law. So what I was trying to say back to this slide, that geotechnical engineer for that NASA project that I stated, he was not a licensed geotechnical engineer. He was a licensed PE, which is perfectly okay. But his report was flawed. And guess what happened? His building continued to go through this process over and over and over again. This very expensive home, I don't know, $4 or $5 million home. It went through this, and it was a large home. So you can imagine what happened. Is this movement, like you're talking about 6 inches movement, some places. So essentially, when you deal with this kind of flaws and defects, you might end up, instead of fixing it, you might end up just removing and replace the entire building because it's going to be cheaper and quicker to do that rather than just, pile foundation here, pile foundation here, level it, and all kind of issues. So I just wanted to share with you that not thank God, great majority of our engineers, their work, their report, whether they're structural or geotechnical, they're great. And if they're implemented, there's no problem. But there are some cases, unfortunately, probably less than 5% that the work product of the design engineer is not the best and can cause problems. Anyways, so going back to this, I just explained. And now we go to geotechnical. If you recall, back in slide 5, we're on slide 13. Back in slide 5, I mentioned to you about these. This is slide 5. Now we're on the third item, geotechnical. Okay, now. Okay, so geotechnical engineering evaluation, as I just stated a few moments ago regarding that NASA scientist home, sometimes are these foundation issues are associated with the geotechnical evaluation, okay? Because the structural engineer does his job properly, let's say, but the geotechnical assumption and the recommendations were not accurate and they were flawed, and that causes a problem. So in general, when the structure doesn't perform properly and it's as a result of them poor performance of the foundation, you can have three factors, essentially three factors. Either the geotechnical engineer was flawed, or geotechnical engineer was flawed, but the structural engineer design was flawed that caused the foundation problems, or both engineers, geotechnical and structural, did their job properly, but the general contractor didn't do the job properly and constructed the different than what it was in the design. So there are these three possibilities. And I'm sorry to tell you that sometimes I see all three combined. I've seen cases like that. Okay. And but 95%, 90, maybe, I don't know, maybe 97% of the construction, they have no problem. They're all good. Very few, that 3%. But that's a lot in our country. Let's say there are about 360 million people, and how many households, how many structures and buildings and commercial, residential, all types. That's a big number. So big loss. So if we say there's a geotechnical engineering evaluation issue, then okay, so this is the geotechnical engineering. So generally speaking, when you are a structural engineer of record for a structure, you have to be very careful who is doing the geotechnical engineering. Let me tell you why you have to be careful, why you have to care, okay? Because God forbid, the way the litigation works in US is that once there's a flaw in a structure, the approach is that the owners, they don't just sue that party that is responsible. They sue everybody: a structural, geotechnical, plumbing, mechanical, contractors, subcontractors, everybody. Why? Multiple reasons. Number one, investigation might find flaws in more than one party that they identified in the very beginning. Number two, they want big pocket because every entity has their own insurance carrier, and it's better than just going for $1 million from one party, going to like 10 different parties for $20 million, just in case. So as a structural engineer, we need to make sure that the geotechnical engineer is reputable. He has sufficient training and experience record, and they know what they're doing. And we need to review their geotechnical evaluation and report. If you find something that doesn't make any sense, you have to question it, because God forbid something happened, you're going to be on the hook too. So we need to be familiar with geotechnical concepts. We don't have to be a licensed geotechnical engineer, but our PE, our training and education enables us to have sufficient knowledge to evaluate these and understand these. So and that's what we need to be careful. Sometimes architects make mistake, and then but mostly geotechnical and structural, they're very related to each other. A lot of structures might not even need geotechnical study, which is different. It's very simple and straightforward. The jurisdictions don't require that, but generally speaking, in California, most of the time they're required, especially if you have hillside condition, which is a sloped property. You need the geotechnical study, geology study. It has to be stamped. The report has to be stamped by a licensed geotechnical engineer and a licensed geologist, both. Otherwise, the jurisdiction doesn't review the plans at all. So let's go back to the next item. So let's go to structural engineering design. See, as I said, thank God, 97% plus of the structures are designed by these engineers, good engineers, geotechnical, structural, and they're good. They perform good. But sometimes, for whatever reason, and a lot of it is not really as a fault of the engineer. A lot of time, I found that as a miscommunication between different design professionals and also construction professionals or the general contractor or subcontractor. A lot of flaws is as a result of miscommunication, not necessarily the structural engineer or geotechnical engineer really did anything wrong. They were good, they were very talented, very skilled, qualified, but something went wrong in the communication. I've seen that a lot. Very quickly, there was a case that I was expert witness in Nevada, Las Vegas, very large facility, warehouse. I don't know, like 100,000 square foot. And they were converting this facility from a warehouse to a indoor agricultural facility. And in order to do that, they needed to have a very specific temperature monitoring inside the warehouse. To do that, they had to run heavy pipes on the roof that had water in them, like anywhere from 12 inches to 2 inches to 12 inches diameter. Long pipe, like 300 feet long pipe. And because of the lack of the communication between the owner, general contractor, and the structural engineer, the roof collapsed because, and who hired me, the insurance carrier for the structural engineer hired us to investigate because he was sued. Everybody was sued, as I said, architect, the structural engineer, even the general contractor, the owner sued everybody. So when we went in, the structural engineer was super brilliant, great structural engineer, and very smart, sharp, very experienced. When we went in and we found out, oh my God, the general contractor never told the structural engineer, no email communication, no any in-person communication that, hey, we're going to these heavy pipes. And these pipes, 12 inches diameter pipes, if you add up the weight, there are tons of weights on the roof and never communicated to our client. Yet he was dragged into this lawsuit. And my experience is the insurance carrier is going to pay something to just get out of it. They don't want to get into the trial litigation because it's so expensive at that point. So they just settled. They paid, I don't know, a couple of $1 million. Every party paid. Like a mechanical engineer paid some, architectural paid some, and general contractor paid some and got rid of it. So sometimes, as I said, it's not because, God forbid, a licensed structural engineer or geotechnical is making an error. Sometimes it happens, but the problems, a lot of problems arise from lack of communication. Okay, now, we were talking about on this slide. Now we're continuing. Let's see, just go back. Okay, structural engineering design. That was we were under the category was okay, under foundation system, A, B, C, D. Okay, now we go back to the slide that I was. Okay, now we are at D. I explained that. Now we are on the structural framing members. This should say 3. I apologize. It should say number 3 because number 2 was foundation, number 1 was general. So here, The categories are subcategories are defective framing fabrication, defective roof diaphragm assembly, impact of adverse events such as fire, excessive heat on various type of structures. Okay, so um, okay, let me. So we talked about uh, general. We talked about foundation. And under foundation, we went through soil, structural, geotechnical, everything. Then now we are looking at the structural framing members. So structural framing members, we're going to find out what can go wrong with the structural framing members. Okay, whether you have a one-story wood frame structure or you have a 10-story, 20-story concrete or a steel structure, doesn't matter. They all have a structural framing members. It can be wood, concrete, masonry, steel, post tension, pre-stress, aluminum, whatever. So, so um, based on my experience, 40 years plus of experience, what are the general issues with the structural framing members? My experience is they can come under these categories: defective framing fabrication, whether it's a steel, light gauge steel, wood, even concrete. You don't fabricate concrete, but you do fabricate the rebar. A lot of cases they bring it to the site. For example, for pile foundation system, they ship them. They fabricate at the shop. They ship them to the site. Okay, all comes under the same category. Next would be defective roof diaphragm assembly, because the structural framing, it would be essentially the beams, columns, and other members. But then you have roof diaphragm assembly. Roof diaphragm assembly, you can have a weather or floor diaphragm assembly. The same in general. You can have wood diaphragm. You can have steel diaphragm with or you can have concrete. Then also impact of adverse event on these general construction material. Let's move on, and I explain to you about the first item, defective framing parameter. Because I don't want to talk about things that are not real, I want to give you a case study, one of our own cases that are in our firm we investigated. This was a California hospital, like 5-story building. And to give you some kind of idea why I chose this case for you is that it's a hospital. And hospital in California, they're, as I think I explained to you a little earlier, they're treated completely different. Only a licensed structural engineer can design this, not a licensed PE. You have to be licensed SE. And the other feature about hospitals in California is that they don't go through the permit process like any other structure. They don't go to the jurisdiction. There's an government entity in California, which used to be called OSHPD, but now the name changed a couple of years ago. It's now called HCI. This organization, governmental organization, they have their own top-notch structural engineers, top-notch architects, mechanical, electrical, all kinds of design professionals, their own team. And they go through the permitting process. They review the plans. And my own experience working with them, I've submitted a lot of plans to them throughout my career, is that if you design just a regular building, residential office, or commercial, you submit it to the city, usually within about 2 months after 1 or 2 cycle of plan check, you get your permit. With OSHPD or HCI for S hospital, that takes you average I think for a hospital or a emergency clinic or emergency center, I think it would take at least a year, 1 year, at least 6, 7 rounds easily. They're meticulous. Their engineers are top-notch engineers. I know many of them. They're good friend of mine, and that's the reason I chose this for you. So it's a little bit more elaborate and more complex than just a simple building. To give you an idea, like if you're designing a the largest aircraft hangar for LAX airport, you don't need to be an SE, licensed structural engineer. You can be a PE and you design this humongous or a stadium. Yeah. So, anyways, the reason philosophy behind it, they want to make sure the hospitals are operatable after an earthquake event or a disaster. So that's why a special attention is on hospitals here in California. We have lots of earthquake, as you know. So what happened in this building that I chose as a defective framing fabrication item? Um, there was defective welding for steel framing. This building was all a steel construction, steel beams, steel columns, white flange, and a lot of moment frame connections. So a lot of the kind of portions of this was fabricated at the shop, and then they were shipped to the site. And then the contractor, general contractor, had subcontractors. The subcontractor had to put them up, assemble them like 5 story. And after they did all the 5 story, the owner decided to bring one more level of inspection because the inspectors from HCI or OSHPA, they came in, they approved, but the owner said, hey, I want my own inspector also come and inspect it. So he brought his own inspector and they found lots of defects. And the defects were all valid. The problem with welding and welding of the moment frame joints is very critical for performance of the moment frame during an earthquake event. So essentially, OSHPAD inspectors they came in, they got involved, they all agreed. And guess what happened? Everything had to get disassembled. The 5 story building came down to the ground again. Everything was opened up, all the everything. They came down to the floor, to the ground. And then they had to implement the corrections, reassemble again. And that's a $5 million lawsuit that I was on the insurance carrier of one of the subcontractors that was fabricating assembly retained me. And we found out that our client really didn't have much fault. The fault was that the shop that they did the fabrication, and my client was in charge of erection. It was not in charge of fabrication. I correct myself. It was in charge of erection. So the problem was not with the erection, it was with the fabrication and the shop. And that's where we were able to identify and divert some of the blame to them. And then, our client still was on the hook, as I explained to you earlier. The insurance carrier had to pay some money. And once the insurance carrier pays some money, you know what happened to your premium, right? It almost doubles. So that's what everybody needs to be careful about, the teamwork. Okay, so going a little bit more deeper to this was that the removal welding using disc grinding instead of arc gouging. So that is a procedure to remove, in order to disassemble this. And because they had to do the disc grinding in order to disassemble this. and that made it more expensive. And also addressing the structural steel well after the steel has been already erected. Now we go to another example because I mentioned to you about diaphragm assembly. In this case, I'm talking about the roof assembly of wood. I picked up also a case that is already settled and legally I can talk about it. It's public information. I don't provide too much detail about the location and so forth, but this is in Washington State. I reside in California, but I travel throughout North America when my clients retain me. This was in Washington State, and it was a dispute between the homeowner, and a general contractor. It was a brand new home. The owner paid for it. It's a large lot. I'm going to check the time. It's 12:07, so we have about 50 minutes to go. I'm going to pace myself because on page 17, I need to go a little bit faster. So to cut the story short, he bought the land. The general contractor came in, built a house, beautiful house, happy, not a small, it's like 4,000 square foot, happy with his family, everybody. And then after a few months, some guests came in, and they made him very, very disappointed because the guest told him, "Hey, your roof is wavy." His roof was not flat. And then he said, "No, I live here 6 months, everything is okay." Then the guest said, "No, you bring an independent general contractor to check." So they brought in the general contractor, and it was wavy, like about an inch or so. So what happened? Why do you get wavy roof tiles or so? Because in case of a wood frame construction, whenever you put these, they put this OSB roof sheeting next to each other or plywood sheeting, they have to have a 1/8 inch gap between them. If they don't, then because of the expansion and contraction due to changing moisture content, they always have these wavy roofs. And I've seen at least a few dozens of these cases all over the place, whether in dry state like here in Southern California or Washington State. I've seen many of these cases. So let's take a look. Okay, this is the picture. I went into the attic. I took these pictures myself, find out what's going on. And this is this OSB against this OSB. You see, they're butted right against each other. There's no gap. It should be a 1 inch in gap. And you see here, I show illustrated here, no gap. So we determined that that was the reason. And once there was a guideline from American Plywood Association that I put it here that you must do this, otherwise you encounter problems. So anyways, that was another matter. And I see that unfortunately, these general contractors, they bring the cheapest subcontractors, and the cheapest contractors usually necessarily don't have the knowledge of this. They just put this over the border on undocumented subcontractors to put this, and they think, okay, it has to be tight, and that's problem. Okay, impact of adverse event such as excessive fire and wood. Why I talk about this here? Because it's not necessarily a defect, but it's a failure, or the title of this presentation is defect and failure. So we talk about some defects. Now we're going to talk about some failures that occur. And these failures are not necessarily as a result of any shortcoming from any design professional or construction professional. This is just nature, and it happens. And we go for investigation, and we just have to have the sufficient knowledge to evaluate this. Okay. Now, when you have wood and you have fire, this is a case study also. I'm talking about this real case study. So you have some real understanding of what happens in case of fire in a wood structure. Okay, so wood generally, when you're hired by the insurance company versus when you're hired by the owner, um, uh, our report should be consistent. We should not say, oh, this wood is okay when we are hired by the insurance company. And then when we are hired by the owner, we say, oh, no, wood is not okay. We have to have objective criteria. Why wood is okay? Why wood is not acceptable? Why is compromised? So there are scientific criteria to evaluate them. And I put the references here at the end of the slide. You will see the references. So wood degrades once it's exposed to high temperatures. And let's go through those temperatures. Okay. So as long as it's below 212, which is the boiling point, the mechanical property of the properties of the wood, they can even be impacted, but it's reversible. They can go back to normal. But once we go above 150, then if it is sustained and it goes also above 212, then there might be some problems. And it depends. As I said here, prolonged exposure to over 150. But if it's more than 212, then obviously it's going to be um, um, more serious. Let's take a look. Okay, so this case study, this is a single family one-story home in Southern California, Pasadena area, and this was as a result of a fire. Okay, now you see these posts, 6x6 posts is completely, you see what's going on. You can't rely on this as a structural uh, integrity is completely compromised. Whether you're hired by insurance or hired by the owner, there's no way you can say this is okay. But you might laugh. I've seen some engineers retained by insurance carrier. They say, oh, just clean it up and put some 2x4 around it and we'll be okay. But that is completely unacceptable and unprofessional. And I've seen worse than those when they're hired by the insurance company. Okay, so here you see the evidence of severe fire and severe temperature on the structural members. These are like ceiling joists here. Okay, and I explained to you what is acceptable, what is not acceptable. Not every wood that is impacted by heat and fire has lost their structural integrity, but there are objective criteria to check. See the discoloration here. Okay, so let me tell you some criteria how to. Okay, obviously these you can't use this anymore, right? Now, when you go in a structure and you want to know if these structural framing were acceptable or not, you have to look at some clues that what temperature this structure experience inside this. Okay, you see here, all the glazings are gone. They all broke, they shattered. What does this tell you? You look at the references that I provide at the end of this presentation, you will see that glazing start cracking above like something about 350 degrees Fahrenheit. Okay. So this tells you what? It tells you that the temperature inside this structure, until it was distinguished completely by firefighter efforts, it sustained that kind of level of degree, like above 300 for a period of time, good period of time. So that's evidence that, okay, whether wood structural mechanical properties were compromised or not. If these glazing were okay, then that would have been a different story. We could a little bit do more investigation to see if we can utilize the existing framing. But in this case, all glazing were gone. There's no way that these okay. Let's go to next a slide, which is the on a concrete structure. This is another real case study, and we were retained by the uh, Department of Recreation in California. It was a wildfire in Malibu, and the trails. We had to take a look at the bridge, steel white line, long span. It was engineered by licensed structural engineer and everything, but it had concrete. It had three components. It had wood railing, wood planks, and it had the steel main members, and it had concrete abutment. And we had to find out if we can certify this or not. So I explained to you about the structural integrity of the mechanical properties of the wood. Same thing here, concrete. Once it goes above 212 degree Fahrenheit, these are all related to the steam. Once the steam comes with pressure, it can impact the way the material properties perform. So once it goes above 212, the cement paste begins to dehydrate, and it loses chemically combined water of hydration, which gradually weakens the paste. So again, the reference number 3 is here. You can look. Again, doesn't mean necessarily once you experience 200, it depends on the duration and several other factors that we're going to go through them together. So we need to do a visual observation. In this case, we had our concrete abutment, and it appeared that the abutments were not compromised. Why? We did visual observation of the surrounding area of the bridge, like the tree vegetation, and we determined that it is obvious that the fire could not generate an environment above 212 for a long period of time. Maybe it was for short, I don't know, a few minutes or a few seconds, but it was not that extensive. That's based on my judgment, my experience, my training. No discoloration of concrete. We have some photographs I share with you. You will see that. Usually, when you have excessive heat, the concrete gets discolored. It can go gray, from gray or natural gray. It can go to black. It can go to pink. It can go to, and it will be obvious. And I've seen those myself in fire events. So we have to check for discoloration. We check for that, and then there's a rebound hammer or a Schmidt hammer. Okay, there are several types of these on the Amazon. You can buy $50. They come from foreign countries, Southeast Asia countries. I don't want to name anything, but if you want the real one, it's made in Switzerland. It costs about $1,500 to $2,000, and they're super accurate. The Prasek brand, I'm not advertising for them. I'm just telling you the most reliable Schmidt hammer that is in existence. And they've been doing this since 1950s. And they are the original Schmidt hammer inventors and manufacturers. So you get those and you use them to see what is the relative compressive strengths. Okay. Now, in this case, we established that they were way over 2,500 PSI. If I was suspicious, I would ask for a core test, send it to the laboratory to do an actual test. Then the next component on this bridge was the steel. We had a lot of steel. We had several steel components, white flange and so forth. And according to AISC publication, as long as you are below 600 Fahrenheit, your steel is okay and not compromised. That's again reference to at the end of this presentation. So I did we did the visual observation again based on the surrounding area. We established that it was not anywhere near 600. So no evidence of warping or distress to the structural steel elements. And now we're looking at some pictures. This photograph is taken by us with our drone. I have a license with the Federal Agency Aviation Administration, and I fly drone. And my associate, who's a junior structural engineer, he's my son. I'm proud of him. He assists me on these site inspection. So from this side of the creek, which is right-hand side, to the left-hand side of the creek, this bridge spans. I believe there were like W24s, and you can see there's nothing left of the railing, nothing left of the decking, just the steel and the concrete. You see the concrete abutment here. So that gives you the overview. Now there are more photographs that's a little more clear. This photograph shows you the steel. This is our client checking something, or maybe my son. I'm not too sure. So this is the white flange secured on the abutment over the creek. And let me explain to you. We went there, I think, shortly after the fire. We didn't go there like several years. We went there like, I think, a month. And look at this, look at this green leaves and everything. This tells you that, okay, if the temperature was really excessive, you would have not had these green leaves here or these here, right? They're all gone. But this evidence suggests that the temperature would have been far less than 600 and probably below 2. Very, very likely that was below 212 degrees. I'm confident that was the case based on my 40 years plus experience and training. And this picture also shows that. And you see this, I don't see any evidence of discoloration on the concrete, any warping, any distortion on the steel. The same thing here. And the concrete is massive. There's probably 5 psi force on these concrete abutments. They're not like sensitive, like a 2000, 3000 psi stress on them. Okay, then here, as you can see, is a 24 inches wide flanges. Oh, by the way, this is the Schmidt hammer. I will show you in a few seconds. I'm measuring the wide flange sections, making sure that the structural as-built drawing that I received, I can compare, make sure they followed the structural engineer, the recommendation, followed his plans. This is the Schmidt hammer that I mentioned to you. And this is the concrete. As you can see, there's no pink or black or anything. And I checked them, different values. This is me. This direction, vertical direction, and check the relative strengths. You have to be careful. If you do this and you find inconsistency, like over 10% or 15% or so, then you have to get core testing sent to laboratory. But once you do it and everyone is consistent, like within 5 to 10%, then you know, okay, this concrete has not been compromised, and the relative strengths that it tells you, like when it tells you like 3000 psi, 4000 psi, it's not super accurate, but it's not very off either. It's relatively, it's reliable. So if it shows you 4000 psi and you send it to the laboratory, it's going to be probably 20 to 25% range of variation. It's not going to be like 90% variation. So if you read 4000 psi, it's well over 2500 psi recommended or requirement. So there are graphs, you have to go through those in order to, depending on the direction of the application of the Schmidt hammer. You interpret them that way. Then Um, Again, on that slide 5 that we had, um, we not the slide 5, sorry, the slide 3 that we had. The fifth item was fourth item is patent versus latent construction defects. We have about 30 minutes, so I try to go through these 18 more, 16 more slides so we can complete this. Use of undocumented foreign material. These can cause construction failures. Erection and fabrication issues, construction sequence. That's method and means in construction. Some of you might be familiar with construction terminology. I have a general contractor license in California. I have like 30, 40 years ago, I did construction management for large projects. So I'm a little bit familiar with some construction terminologies. You don't have to have a general contractor license to understand this. These are simple concepts. Poor workmanship by subcontractors and defective and temporary supports. So these are the main sources of the problems that I've seen over the course of my career. So undocumented material, what are we talking about? Okay, like before 1990s or 1980s, all the steel beams, rebars, and so forth, we were using in US. They were made here or in Canada before 1990, I think. But then gradually you started receiving, with the construction boom and shortage here, we gradually started receiving from Southeast Asia. I don't want to name any country, specific country, received from them. And unfortunately, the quality control on those regions, not very high, and a lot of these construction materials, they are substandard. When you send them to the laboratory, you'll find out that they don't meet our requirement, but there's ASTM or other standards. And use of them without testing them first is not wise. And even today, you continue to receive undocumented foreign material. Sometimes they send their laboratory testing, but those laboratory testing are not done in US. They're done in their own origin source country, and I don't trust those laboratory testing. I'm still on a case. It's a $30 million lawsuit for a very large, very expensive home, and they were importing a lot of undocumented material from, again, I don't want to name the country, a country in Southeast Asia, which gives us we import a lot of material from them, and essentially those materials caused these $30 million lawsuit. And they were not checked, they were not tested. And later, when the defect surfaced, when they were checked, we observed that they don't meet a lot of requirements that we have in US. So one thing that I strongly recommend when you're wood material, we don't have to worry because they come from Canada and we can rely on them. But steel, when you have a steel structure, I strongly recommend you check the documentation from the manual, from the supplier, to provide you that. If they're suspicious, then they shouldn't be purchased, because the general contractor usually, they bid on the fixed price. They want to go with the cheapest, but you're going to be in trouble if they do that at the end. You don't want to be a victim. A general contractor doesn't care if they have 20 simultaneous lawsuits. They don't really care. Do you think they care? No. You care because you're a licensed engineer, and your license will be uh, a big issue. You have to fight with the board to prove that you had no problem. If the settlement, or if your insurance carrier settles it for you more than, I believe the amount is like $40,000, it has to be reported to the Board of Engineers. This is how it works in California. And once it's reported to the Board of Engineers, they start an investigation. They open an investigation for you. So you have to be extremely careful. For general contractor, they don't care. They don't have such a process. Insurance carrier pays for this. Okay, his premium goes up. He doesn't care. You go next job, next job, next job. I know some general contractors that they have like 20 simultaneous lawsuits. They don't care. They don't worry about anything. They're not paying anything. Just continue. Their license is not questioned, nothing. Nobody accuses them of, God forbid, negligence, incompetence, growth, negligence. So we are different. We are design professionals. We need to be extremely careful. If a contractor, general contractor, we can't go to cheap, extremely cheap and suspicious material, don't let them do that. Don't approve that. Okay. Construction sequence, next item. That can determine some impact some of the issues. I explain to you in a few moments if we have enough time. Poor workmanship doesn't need to be explained. Defective temporary support. Temporary supports, whether your temporary supporting the framing or temporary supporting an excavation, usually they have to be engineered. Generally, they have to be engineered. Whether excavation is supported or some framing is supported, it has to be engineered. They can't just put a 2x4 or something in the contract and say, oh, this is good. No, they have to. There are certain regulations, certain building code applies to these temporary support, whether it's less than 180 days and so forth. Okay. So we continue on destructive testing. The reason I put removal of wall and ceiling finishes here under destructive testing is that almost 99% of general contractors, lawyers, construction defect lawyers, and even engineers, they think as soon as you remove wall finish to examine the structural framing, you already committed and you already performed destructive testing. That is wrong. Removal of wall finishes are not, they don't constitute destructive testing, even though it's common. Unfortunately, everybody sees it that way. As I said, even a lot of structural engineers that are not specialized in forensic investigations, they think that's, and as soon as you start doing this when there's a litigation, they panic, everybody panic. Oh, you did destructive testing, you should have our permission first. No, it's just a removal and to examine what's the framing behind it. Core sampling, yes, that's a destructive testing. What is the definition of destructive testing? The term itself is explaining that. It means you take a piece of sample from a structure, whether it's a concrete or a steel or rebar, you take a piece out. Then you take that to the laboratory, you test that component to the destruction point. It has to be destructed in order to provide the mechanical properties. It has to be destructed under the test. Otherwise, you can't have those values. That's why it's called destructive testing. And that material, whether it's rebar, a piece of a white flange, or a concrete, once it's destructed, they throw it away. So that destructive testing is going to be involving removal work. If a piece of concrete, piece of rebar, piece of steel is removed, a licensed engineer had to provide the repair methodology, repair work to repair that portion. So keep in mind, I put it here just to point out to you that this is not removal of the finishes does not constitute and is not defined as a destructive testing. If somebody tells you, just give the explanation that I told you, destructive laboratory. Non-destructive testing. Non-destructive testing, manometer survey, moisture verification, Schmidt-Hammer verification, GPR, vibration monitoring, ultrasound distress measurement, resistance, tachometer, crack monitoring. These all constitute non-destructive because you tested without any damage to the original material and without taking anything out. And obviously, whenever these are done, if it's a litigation, all parties have to be present. If it's not litigation, it's just an investigation for insurance or for a private client. No, not all parties need to be present. Usually, it's okay, you do it yourself. Going to patent versus latent defects, cracks in concrete generally come from two sources. Either they come from shrinkage or they're really structural cracks. If they're shrinkage cracks, there's no concern, okay? But if there are structural cracks, there are issues for those. And you need to be able to distinguish what's the difference, which crack is shrinkage and which crack is not. And is okay. So this guideline, ACI, provides you that information against reference for to calculate the shrinkage. It depends on many factors: the concrete, the strength, age, the rebar, the water cement ratio, and so many things to determine what is the acceptable crack widths and lengths for shrinkage and what is not. Once it goes beyond shrinkage crack, like for example, you have 1/4 inch width crack, it can't be, doesn't matter. The general contractor tells you, oh, don't worry about it, it's not any problem. No. Once it goes beyond certain width, it's a structure and it had to be investigated. Doesn't mean necessarily it's unsafe, but it has to be investigated by a licensed structural engineer to determine whether the structural integrity was compromised or not. You go to another case, which we have about 13 slides and we have about 20 minutes. Another case study in San Francisco.